First, we open Maya and start with an empty scene. To help us get to know the functions of the exporter, we'll first create a simple cuboid. We'll start by looking at a function which helps us split an object into multiple objects. Before we begin, we'll need to open the outliner, which is found in Menu, Window, Outliner. Then we select our cuboid and switch into Face mode by right-clicking on our object and choosing the Face option. Now we can select the individual surfaces of the cuboid, which are highlighted as we move our mouse over each of the surfaces. Next, we open the i3D Tools window. Then we select the front and a side surface. In the Tools tab, we go to the Mesh Tools category and click the Detach Faces button. As we can see in the outliner, our cuboid has been split into two objects. We now come to the second part of this chapter. For this, we begin by opening a new scene. We'll now take a closer look at the pivot of an object. Ultimately, the pivot indicates the position of an object and is its center of rotation. It is therefore of the utmost importance for objects that are to move later. For cylinders, the pivot needs to sit at the base, with the local z-axis pointing along the length of the cylinder. This is necessary for us to be able to align the cylinder correctly later. For the following steps, we're going to need two cylinders. So let's create the first cylinder. Once we've created our first cylinder, we can go into the menu and click Edit, Duplicate to duplicate the cylinder. Now we scale the duplicate slightly and move it upwards. To make sure we have the correct hierarchy, we select the smallest cylinder with the left mouse button. Then, while holding down the middle mouse button, we drag the small cylinder on top of the large cylinder. Now that we've created our cylinders and grouped them together, we'll switch modes via the Insert key so as to be able to move the pivot of the object. We can then move the pivots to the desired positions. In our case, this means shifting the pivot of the first cylinder to the bottom at its base, so the point at which we want the cylinder to rotate around sits at its origin. We then move the second pivot to the origin of the second cylinder. Now we open the Attribute Editor and switch to the corresponding tab so that we can set the position. We should take note of the value for the Y position of the cylinder. Now we need to click on Freeze to Pivot in the Giant's i3D Tools window and see that as a result the positional information of the object has changed. The next step is to correctly align the pivots. The Giant's i3D Tools also has a function for this. First, we create an auxiliary object, a transform group. We position this child object under the second cylinder by dragging it onto the cylinder with the middle mouse button held down. We do this in order to accurately and quickly adjust the position of the auxiliary object relative to the cylinders. Finally, the element should be placed at the end of, or effectively at the top of the cylinder. To help us follow the following steps better, we'll quickly switch to the panel for the tool settings. This can be found either on the upper right by clicking on the symbol of a wrench or by double-clicking on the icon for the Move tool here on the left. In the tool settings, we can then activate the Object option in the Move axis. So we first select the main cylinder while holding down the Control key and then select the auxiliary object. Now that we have selected both elements, we can recalculate the orientation of the pivots by clicking on Align Z-axis. As we can see, the rotational information of the cylinder has changed, and the pivots of the cylinder are now aligned so that their Z-axis lies along the longitudinal direction of the cylinder. To illustrate this again, we can manually set all rotation values to 0. The cylinders are now orientated in the direction of the global Z-axis. So our attempt was successful, and now we can leave the alignment of these cylinders as they are, where they could be incorporated and used in a hydraulic system for a lift on a trailer or on the rear hydraulics of tractors. Speaking of tractors, a vehicle is typically made up of at least one physical component, which acts as the body for all the collision calculations in the game. Our cylinders, however, should have no physical significance. To ensure this, we begin by selecting all the parts of our cylinder in the outliner and then switching into the window for the Giant's i3D tools on the Attributes panel. Here we can set a variety of properties for the object. Some properties affect the calculations of the physics of the object, whilst others affect the rendering, altering how the object appears in the game. We can leave most of the properties as their default values. However, we still need to apply these settings to our cylinder, so we click on Apply Selected below so that the settings chosen in the outliner are applied to our objects. Now we have communicated to the exporter that the objects are to have no physical significance later. This is evident from the fact that here in the rigid body section above, we have no elements selected. But we still want to take a quick look at what elements there are and what they do later in the game. In principle, we can distinguish between 3 different types of physical objects. First, we have static objects. Static objects are, for example, houses, fences, or trees. These type of objects do not move under any circumstances and are therefore called static. The form or object that is static can be any shape, an interesting contrast to the other 2 types of physical objects which cannot. The second type of physical objects are called kinematic. Kinematic objects are not dynamically simulated, but they can be moved using a script. A good example here would be gates, which you don't want tractors driving through, but you do want to be able to open. It is important to note that kinematic objects must always be convex. The third and final type of physical objects are called dynamic. As their name suggests, dynamic objects react dynamically to other physical objects. Ultimately, all vehicles are dynamic objects, as well as bales. As with the kinematic objects, their shape must also be convex. However, there's a way to create more complex forms for a physical object. First, we need the Attributes tab in the Giant's i3D tools. In it, we find 2 checkboxes with the names Compound and Compound Child. These fields are used to effectively weld 2 items together. So we open a new scene and create a cuboid. Suppose our cuboid was to be the collision body of a tractor. Perhaps we would like to have collision sets for the chimney and cabin too. To do this, we create 2 more cuboids in the appropriate sizes. It is vital that once we've scaled the objects, we click on Menu, Modify, Freeze Transformations. This fixes the scale values to 1, which is important when it comes to giving the object their corresponding physical properties. To effectively set up this complex physical formation, we first select the main body, then set it to both dynamic, and compound to indicate that this is a physical object that other objects are attached to. However, in this case, the relative position and orientation of the objects cannot be changed. We can then set the two cuboids for the chimney and cabin hierarchically below, or in other words, inside the main cuboid. Now we select these two objects in the outliner and activate the option Compound Child in the i3D exporter. Thus, the objects become physically relevant. In other words, they are now part of the physical form of the main body. In this way, the effective nesting of objects can be used to create almost any type of complex system by simply joining objects together. Finally, we'll take a look at another useful option when it comes to rendering. The clip distance indicates the distance after which an object is no longer visible. This helps limit the computational load and helps maintain a fluid level of detail. Typically, we set the value to between 300 and 350 for vehicles. It should be noted that the clip distance is also inherited hierarchically. For example, if we set the clip distance of our main body to 100, for example, then the bodies below will also be no longer visible from this distance. However, we could reduce the clip distance of the lower bodies even further, to 50, for example. While initially it may seem counterintuitive when we consider the small details of a vehicle, such as the interior of the cabin, it makes perfect sense.